I think there were some technical issues to which we were not able to hear our voices. So let us start it again. So, hello everyone, I'm Sparsh and I'm having my colleague Anurag with me, and we are going to discuss a chat microservice architecture that we have developed. Okay, so Anurag, can you address us with today's agenda? Hello everyone, I'm Anurag. So, today's agenda. I think there are some technical issues. Let me get back to you people. Hello everyone. There were some technical issues we were facing on the presentation. So we should start it again. Sparsh, sorry for the trouble.
Hello again, so I'm Sparsh and I'm having my colleague Anurag with me, and we are going to discuss a chat microservice architecture that we have developed. Okay, so Anurag, can you address us with today's agenda?
Hello everyone, I'm Anurag. So today's hello. Yes. So today's agenda of the webinar is proposing a chat microservice architecture and what made us creating a new one. Understanding the tech stack behind and why we have used one. Cost of deployment, proposing two types of deployment systems. So depending on the user base, we can choose any one. At the end of the slide, we would like to present a small demo on the chat application.
Okay, so Anurag, so what should be our expectation from this session?
So the expectations from this presentation would be, we will be going to propose a chat service architecture. We will be sharing what made us design a new service, tech stack behind the service and why, the cost of deployment and different strategies, features that could be supported using this architecture. And in the presentation, there would be no coding involved. Moving towards the introduction of the webinar. In today's trending world, when it comes to designing a new application, a chat service is becoming must-to-have service. The chat service may be in the form of customer support, community chat service, or a fully fledged chat service to support all the features like a modern application does, like WhatsApp, Facebook Messenger. Having such kind of service, we have two options: creating a new service, which involves high cost in terms of development, time, and testing, or we have an option of choosing third-party service, which always gives us a hard time in customization. Thus, we end up spending a lot of efforts in that chat service rather than the main application or the master application in which we will be using this service. So we tried to come up with the chat service architecture that could be easily customized and could be used in various applications. The service is scalable, so depending on the load, we can easily scale up and down the service. Also, the service provides a support of fully fledged chat service, which includes one-to-one chat, group chat, media share, etc.
Okay, so the idea seems interesting, but Anurag, can you tell us what made you to develop this particular service? I'm sure there must be multiple third-party services in the market that can provide the chatting mechanism in the same way. So what is the logic behind this particular service?
Here at our organization, Sustainable, we design various kinds of applications where we require a chat service. We have been building the service with respect to each application as the requirement of each application differed from each other. So we came up with the idea of designing a chat server which, one, could easily be used in various applications and can be scaled up depending on the load and user base. Second, the service should be designed in a generic way to support different types of applications and their requirement. Third, we wanted a service to be very robust so that same service could be used in real-time multiplayer games also. Fourth, the cost effectiveness of this service. So depending on the user base, we can decide the deployment strategy of the service. So the single deployed service should be supporting various kinds of applications at the same time. So I mean to say there is a single hosted service which could support different clients at the same time. 6. Storing data at our premises.
Okay. Okay, Sir Anurag. So as an engineer, I'm keen to know that tech stack behind the architecture and why the technologies in the architecture you have chose them. So can you tell us about the tech stack behind all architecture?
On choosing the tech stack, we have tried to come up with the lightweight and high performance services and applications. On the backend, we choose Node.js as a server, which is an event-driven, non-blocking input-output model that makes it lightweight and efficient, perfect for real-time applications that run across the distributed devices or servers. Socket.io enables real-time, bidirectional, and event-based communication. It works on every platform, browser, device, focusing equally on reliability and speed. Socket.io provides a socket through which we would be sending data from clients to the server. Sequelize as an ORM tool for Node.js. It supports various dialects like PostgreSQL, MySQL, SQLite, MS SQL, thus providing us flexibility to choose different types of database just by using the dialect. Redis as our in-memory data structure and cache. Here, we have used Redis to store frequently accessed data and also use it as a message broker for sending messages between two servers. On the cloud, side, we have used AWS as a service provider. On the AWS end, we have used EC2 instances. In the EC2 instances, we will be running the chat service. AWS provides different instances types through which we have a flexibility to choose among various CPU, memory, storage, and network capacity, depending the type of application we want to host. As a database, we have used Amazon Relational Database Service, RDS, which makes us operational and maintenance cost optimized service, and it reduces the time consuming in administration tasks such as hardware provisioning, database setup, and patching and data. Elastic Cache as a hosted Redis server. So for the Redis, we have used Elastic Cache, in which we will be storing frequently accessed data. For all the media file transfers, we will be using S3 buckets. Application load balancer, which plays here a very important role. It serves as a single point of contact for clients. The load balancer distributes incoming application traffic across multiple targets, such as EC2 instances, in multiple availability zones. This increases the availability of our application. For the deployment purpose, we have used Docker, which helps us in deployment and makes our task very easy. Using Docker, we could easily deploy the server, thus help us in setup of new instances very fast.
Okay. So Raj, here I'm having one question. So can you tell me why you have not gone for a NoSQL database? Because there are technologies like Node.json, Socket.io, which are compatible with NoSQL databases more. But you have chosen here a SQL database. So why is it so?
Actually, first, we did not find any good reasons to move to a NoSQL database. We have spent a lot of time in designing the database schema and finally came up with a structured model for storing the database. Also, the max size of NoSQL document is 16 megabytes, and here in SQL there is no limit, so we can store any amount of data in the database. And since we have used RDS as a hosted database service, so it would be very easy to upgrade the database instances as per a requirement.
Okay. So the tech stack seems powerful. There is some powerful technologies listed over there. I'm sure you have integrated these technology in some architecture or topology. So coming to the most important part of the webinar, can you explain the architecture of the service to us?
Okay, Spurge, after a lot of research and studying the architecture of the application, like WhatsApp, Facebook Messenger, we came up with the following architecture. As we can see, each and every client is connected to the application load balancer, from where the load is distributed to various EC2 instances, where the chat server is running. Whenever if any EC2 instance goes down, application load balancer start distributing the load to other instances. We are running the Node.js servers inside the EC2 instances. Each server is completely independent from each other. If one of the servers goes down, the other servers will not even know it. Only the application load balancer will redirect the request to other instances. For the database service, we have chosen RDS. The database is used to persist data like messages for a peer-to-peer communication, group chat, and media-related storage or information. We are persisting the data in the database only in a sync way, thus making sure that we are not delaying message delivery. Elastic Cache. As a hosted service for Redis, we are using Redis as a publisher and subscriber to send messages between the different servers and also as a cache to store frequently accessed data. For example, array of group member. If we want to send any message to a group, we easily fetch it from the Redis and get the group members and then directly emit message to the group user.
Okay. So if we talk about any architecture, so there are some key factors that needs to be, examined before using architecture. So like there is fault tolerance, robustness of architecture, scalability, bidirectional scalability of an architecture, performance optimization, and most important, the cost effectiveness. So can you elaborate these points in terms of your architecture?
Yes, Sparsh. Talking about fault tolerance, we have different servers, the EC2 instances. Each EC2 instances are independent from each other. So if one of the servers goes down, the application load balancer will redirect the traffic to other servers. Client will not even notice what has happened at the backend. This way, the client gets reconnected to other available server. This is how we are making a system fault tolerant. So here the actor is application load balancer and we are creating stickiness of the client. Also, depending on the load, we can create replicas of these instances, EC2 instances, I mean to say, and also if there is load on specific service, for example here, the database is behaving slow. So AWS provides very good flexibility to increase the instance size on the go. So we can easily upgrade the service. Same applies for the Elastic Cache. And if we do not require massive servers or massive database, so we can easily degrade or downgrade the services. So this is how we can easily customize the architecture depending on the load. Talking about the message delivery flow, each and every client gets connected to application load balancer which distributes the load. When a client gets connected to any instance, a entry is made in the Redis having the client's ID as the key and instance ID through which it is connected as a value. Now let us see a scenario. Client A is connected to server A and wants to send a message to client B, which is connected to server B. When client A sends a message, server A uses Redis to get the server's ID through which the recipient of the message is connected. If the recipient of the message is connected to the same server, the message is directly emitted to the client using the socket object of the recipient stored in the instance memory itself. Or if the recipient is connected to some other server, the server A will emit a message to the recipient server, and from the recipient server, the message is directly emitted to client B. So this is how the data flow is happening in the system. Also, one important point, When using the application present in market, they simply try to use Redis adapter in which each and every message flow to the elastic cache itself. We have optimized that situation. In this, we just fetch the server ID through which client is connected. Suppose if client A and client B both are connected to same server, server A, there is no need to transmit that message to elastic cache, and we have avoided that round trip. In this case, if both are connected to same server, then the message is directly emitted from the client A from the local socket object stored with respect to client B. So this was our data flow.
Okay. Okay. So the architecture looked promising. Now, can you explain all the features that your service provides?
Okay. Talking about the features, one of the main important features was easy deployment, from which we came up with an idea to building this architecture. So for deployment purpose, we have to easily integrate the socket IO SDK in our clients, and we can simply connect to that socket and create some listeners and start listening and emitting the events to the server to and fro. This is how we can easily integrate the service. So there would be a master application in which this microservice will be integrated, and authentication part related part will be handled by the master service itself, and all the communication related stuff will be handled by the chat service. Second, different application can be supported from a single deployed service. Say there are two services. Say one is football and one is cricket. If football users don't want to see the cricket users, they can be deployed on a single server, and both the users will be of different namespaces. So user one, sorry. So user one, that is the users from the cricket server, would not see the users of football servers. In-house data storage. In this service, we have stored all the data inside our premises. This was our concern. We don't want to store the data on the third-party application. So we decided to store all the data inside our premises. The service is lightweight, this cost effective. In terms of cost effectiveness, I mean to say there are different type of applications, scenarios, and user base. So depending on the user base, we can easily customize this architecture so to support different type of applications in a cost-effective manner. I will be explaining this on the upcoming slide a little more. In terms of scalability, we have already talked. Each servers are independent from each other, so we can increase or decrease the services, and each service are designed in a microservice architecture way. So say there is a load on elastic cache, so we can easily upgrade that particular service instead of replicating or increasing the infrastructure of overall service. So we can easily upgrade a single service itself. Easy customization. In terms of customization, we have to add some more sockets or remove more sockets. That's matter of few minutes. We want to have that X service or not. We have to decide, and we have to just listen that socket event. By default, this This chat service supports text messages, file, emojis, and many features that a modern application does.
Okay. But Anurag, if I think from a client's perspective, the cost is an important factor. So I want to know how much will it cost me if I want to install this particular service for my application.
As we talk, this service is fully customizable. So here what we have done to reduce the cost, we have used a single EC2 instance. And in the EC2 instances, we installed services like Nginx, which has replicated application load balancer, a node server, a Redis in replacement of Elastic Cache, and MySQL database in the EC2 instance itself. So here, application load balancer is replaced by Nginx. Thus, Nginx will be acting as a single point of contact between the client. So each Nginx will connect to the node server, that is a chat service, and chat service will connect to Redis and MySQL database internally inside a EC2 instance. And the cost of this would be $40, which includes one T2 medium instance and one S3, which has 1 GB of capacity for storing media files. But that was not production ready. Talking about the production ready, we have to bear some extra cost. The previous architecture would support some small clients or say user base of 100 to 1000 users. In this production ready, we have used application load balancer to T2 small instances, that is EC2 instances, RDS, D2, DB, T2 small, Elastic Cache, Cache T2 small, S3 of 1 GB storage, and application load balancer. So this will cost around $92 per month. So in terms of cost, these were the two topologies in which we can deploy the service.
Okay. So the cost seems to be pretty moderated for a chatting service that is easily customizable. But when we talk about any production ready system, it's not about its development. We need a DevOps which will be responsible for the deployment of the code and the server security. Regarding the deployment, I have some question for this service. How long it will take this service to get deployed on a production ready server? How much DevOps efforts it will need to deploy this service, and how much maintenance and monitoring it will need after we have deployed this service? So please, can you answer these questions?
In terms of deployment, it might take nearly 30 to 40 minutes deploying it on the staging or development environment. And 30 to 40 minutes include the setup of Nginx, Docker, and other services like databases. Our services will be installed or set up just by using sudo docker compose up. That is so simple. We have to just put this command and execute. The service will be up within 1 to 2 minutes. Other is the cost of deployment, setup of Nginx and S3 buckets. In terms of production, it might take up to 4 to 5 hours, which includes the setup of application load balancer and buying new servers like EC2 instances, S3, and then connecting to each other. But in terms of starting and spinning the server up, it takes nearly 2 to 3 minutes. So you ask, do we need a DevOps guy? Yes, we need a DevOps guy, but with a little knowledge, not that enterprise level DevOps guy. A normal DevOps person could easily deploy the service. Maintenance. In terms of maintenance, it depends. If we have already configured the application load balancer correctly, there would be no cost involved in maintenance and monitoring the service. The application or the architecture is itself so much robust that we don't need any monitoring.
Okay. So 30 to 40 minutes is insane. Like I remember my days when, I have to deploy a production ready service and it will take weeks from DevOps going back and forth to them and, deploy a particular service. But now Docker and Kubernetes made our life easy. So it's pretty easy to deploy a service on a production ready environment. So that's made our developer life easy. Okay. So coming to the next thing, so every solution has its own pros and cons, and your service should not be an exception. So being honest, can you address some of the pros and cons of your architecture?
First one is it's lightweight since we have used Socket IO, Node.js, Elastic Cache, so it is very lightweight in terms of the services we have used. It supports real-time message delivery since we have used various kind of services like Redis as PubSub mechanism. We are saving the data in a sync way. So this provides real-time data delivery. Easy integration, as we earlier said, we just have to integrate the Socket IO SDK and start emitting the events and listening the events. We don't need any other configurations on the client end. Scalability. In terms of scalability, as we have seen in the architecture, each component is independent, so we can easily scale up and down a particular service in which we are facing load. Efficient. As we said, here each and every message is not being traveled to the Redis or the adapter through which messages are being transmitted to n number of servers. In this, if the sender and the recipient of message connected to the same server, the message being emitted from the local socket object stored in the instance memory of the server itself. So the round trip of the message is avoided. Highly customizable. We can easily add some new sockets, events, and there are different namespaces. For example, if you want a simple server through which we can emit message to client server in terms of the master application. If master application wants to push some message to clients, so there is a namespace for servers, there is a namespace for users. So in this way, we have divided the sockets and their events on different namespaces. A service is ready to be used for one-to-one chat service, group chat, online net play game, automatic reconnection. This was one of the main issues we were facing when we tried to come up with a solution, but we have avoided that using services like application load balancer, stickiness of the session, and there are some events to maintain client connection. By default, the media sharing is enabled in a system. Talking about the cons of the service, comparatively, It is a new service present in the market. We might need to write some extra code on client end to detect network drop. This always gives us a hard time when dealing with the sockets. There is no way to detect who dropped, the server dropped and or client dropped. So we tried to avoid that using our architecture. The message storage could grow very large in X amount of time. So we we do not have any features to archive that message and store them into the S3 bucket. So these were the cons of the service.
Okay. So, like being a developer, I can understand. So you and your team must have faced lots of challenges during the implementation of this architecture. So can you share some of the challenges that your team has faces while developing this particular service?
Talking about the challenges, handling client connection drops and slow network really give us a hard time. Designing our architecture to support multiple applications from single deployed service. Managing delivery notification. That is, when some ex-user is offline and some message is being sent to that user, the message status remains unread but delivered. And when he comes online, all the messages from the database are picked one by one and sent to the client, and the status of the messages are being changed to delivered. So we have tried to come up with a generic solution for both group chat and peer-to-peer communication for the delivery notification, delivering the group message in real time. So we tried to store the group members inside the database, but when sending the message to the users, we were facing a small delay. So to avoid that delay, we chose Redis as in-memory data to store group members of a group, and here we can easily search the group name and their respective members, and from getting the respective members we can directly emit messages to the group members. So using Redis we were successful in delivering the group messages in real time, creating a scalable architecture which could be easily scaled up and down depending on the cost. So we can easily add or remove some components from the service itself. Flexibility to replace component depending on the cost, like we have represented two architectures in terms of cost of deployment. So depending on the cost, we could easily replace application load balancer with Nginx, RDS with a small server who say a small server installed on the EC2 instance itself. This is how we have reduced the cost on deployment.
Okay. So far so good. But if we talk about the further scope, so Anurag, can you share your plan to extend this service? Like what can we expect from this particular architecture in future? What will be the features that you are planning to add in this architecture?
Talking about the features that we could include in the upcoming releases, one is feature of media files upload. Right now, we are directly uploading the files to the S3 bucket and then emitting a message containing the URL of the image or the media file to the server, and through which each and every client gets and downloads the image from S3. So we want to replace this and we want to use the socket, and from the socket we want to emit that image using the socket to the server, and from server we want to upload the file directly to the S3. Better handle of network drops. We want to better handle some network drops. Provide different rotational encryption policy for messages. Keys should be automatically updated over the time period. Handling message archiving and storing it to the S3 bucket. Say archiving the message which are older than S3 bucket. Here now we have to do it manually, but we are planning to have some automated service which will remove the message or say archive the message from the database and ship it to the S3 bucket. So we have prepared a small demo of a chat application. We are just sharing a screen. Here is a React Native application. So here is a React Native application in which we have prepared a demo client. Here, there is a list of users through which we have already done chatting. Here is a list of active users through which whom we have not done chatting. From this menu, we could see the users to whom we have logged. Here is the block user list from where we can unlock a user. Now again coming to the inbox screen. This is how we are sending messages to each other. Notice the message is being emitted in real time. Also, on the left mobile, we can see an event is typing. So these kind of features is also integrated in a service. We want to send some media files over the socket. So we have selected a file and see. We can see it in real time. We can delete a message easily. Now we have brought that user. Now we will not able to send a message. Now we have unlocked it and we can send the message in real time again. Only the sender of the message will be able to delete that message. Arizona here is a group. It has these members. We can make users as admin on single click. Now we are removing the users from a group. The list is being updated at real time. Now to add members, we could easily select the members. Here we want to get a group. In the left mobile is the admin, so we can delete the group. Sorry, it's the owner of the group. The owner of the group has a functionality to delete a group. This is how we could create groups. Now we can upload the group profile picture. So this was our presentation on the chat service architecture. If anyone has a question, please shoot us the question. We would be happy to answer that.
Okay, so Anurag, I guess we have our first question, which is, can this service be extended to support chatbots?
First, right now, we can use some components, but as a chatbot, the AI engine is not integrated here. For that, we have to use some other service or a master server through which we could easily receive message and send message with respect to the kind of answer we are expecting in case of a bot message. So we have a namespace for the servers, but we don't have any AI server here.
Okay. Okay, so we have a second question. So, do you have any history saving mechanism? Okay, so let's say I should explain you the question. So this user wants to, I guess, wants to ask like, do we have archiving mechanism in our service right now, or are we planning to do that?
Okay, for archiving, we are planning to do it in the next upcoming releases. We can do it manually, but I think at present there is no need since SQL database and that too as a hosted one, has a support to accept and store large amount of data without being archiving. If over the years it gets slow, we can simply archive some older messages and emit and bundle them up and store in the S3 buckets.
Okay, so another question. How easy it is to integrate this with another modular application?
So the whole idea was to design the service was easily integrate the service. We just have to integrate socket.io SDK in our client, and we should easily start listening to some events and start emitting. Thus, we could easily integrate the service to the existing master service.
Okay, so one more question. Okay. So, will I get the data, my data across multiple devices? Okay. Yeah.
Okay. Yes, we could easily get data on multiple devices, but we have to sign in into a device one at a time. So there would be no two active sessions. Suppose if we have logged in inside one application, we should be logged out from the other servers for the same application. And in our case, since we are storing the databases at the server end, so we could easily emit that message to other devices also. So when user wants to access his data from other servers or other mobile devices, we could easily transfer that data to that device also. And for each client, we would treat him as a new client. So we could easily transmit his data or history to him.
Okay, so I guess there are no more questions from the audience. But still, let's wait for half a minute. Okay, so I guess there are no more questions. Okay, so guys, that's it from our side. We are thankful to you for joining us today and hope you enjoyed the presentation.
And sorry for the trouble everyone faced at the starting of the slide. Thank you everyone. Have a great day.
Bye.